In this video, I am going to discuss how to solve question 3.45 from this book, Physical Chemistry by Laidler, Mazer, and Sanctuary, the 4th edition. First, I would like to discuss a concept known as fugacity. Fugacity is used for non-ideal conditions. As the pressure approaches zero, the fugacity and the pressure become more equal and the gas becomes more ideal. As we do our calculations, we want to make sure that if we are not working with an ideal condition, that we use the proper equations that have the non-ideal conditions worked into the equation. This top equation is the one that we use for ideal situations. Our Gibbs free energy is equal to the moles times R constant times temperature in Kelvin times the natural log of the final pressure divided by the first pressure. For non-ideal conditions, we are going to use this other equation in this question that we're going to work out today. And that is that the Gibbs free energy is equal to the molar volume times the change in pressure. You can use this equation when you have 1 mole in a non-ideal condition with no change in temperature. To find our molar volume, we are going to divide our molar mass by our density. And the reason why that works, if you look at it like this, molar mass is grams per mole. And density, this is going to be upside down because we are dividing by it. Density is going to be grams per some volume, like liters. And if we were to cancel out our grams and our grams, we would end up with liters per mole. And that is our volume per mole right here. Okay, so now that we understand what equations we are going to use, I'm going to go over the question we are going to address today. Question 3.45 is calculate the change in delta G sub m in the Gibbs energy of 1 mole of liquid mercury, initially at 1 bar pressure if a pressure of 1,000 bars is applied to it. The process occurs at the constant temperature of 25 degrees Celsius, and the mercury may be assumed to be incompressible and to have the density of 13.5 grams per cubic centimeters. Now, the answer that the book gives us is 1.485 kilojoules per mole. And what I did was I went ahead and wrote out everything that was given, and that is that our N is equal to 1 mole. We are dealing with liquid mercury. Our first pressure is 1 bar. Our external pressure is 1,000 bars, which in this equation, we are going to treat that as our second pressure, so our P1 and P2. Our delta T is 0, which is one of the conditions for us to be able to use the equation that we were going to work with in this situation. And our temperature is 298.15 Kelvin. We are looking for our molar Gibbs energy. This is how we are going to set up the equation. So we are going to do this equation right here. And the first step that I would recommend is to find your molar volume. And then after that, we are going to find our delta P, and then we will put them all together. So like I discussed, our molar volume is just our volume per mole. And the way that we are going to find that is we are going to use the known molar mass of mercury, which is 200.6 grams per mole, which I found from a periodic table, and the given density of mercury, which is 13.5 grams per centimeters cubed. And we are going to divide those just like this. So our molar volume is equal to 200.6 grams per mole. And then we are going to multiply it by the reciprocal of the density since we are dividing by the density. So 13.5 grams goes on the bottom and centimeters cubed goes on top. Now I like to be visually organized, so I use a lot of colors, and I like to go ahead and cross this off so we can see what we are working with. The grams cancel. We have moles on bottom and we have a volume on top. And if you were not aware, centimeters cubed is a distance cubed, and a volume is also expressed as a distance cubed. So I'm going to go ahead and change back to my original pencil. My molar volume, if you were to put this into your calculator, would be 14.859 centimeters cubed per mole. And because we are looking for ultimately joules and then kilojoules, it would make more sense for us to go ahead and convert this to meters cubed at this point, because whenever we are trying to convert our pressures and volumes into joules, it is always easier if you are starting with units of meters and newtons. Because 1 joule is also equal to 1 newton times 1 meter. So the way that we are going to do this is, you may remember that there are 100 centimeters in every 1 meter, right? But we must also remember that we are going to cube it. So everything in here will be cubed, and so will everything in here. And if you don't want to write the 1 as a cube, you can also just write it like this. Okay? And then I'm just going to cancel out my centimeters cubed. We end up with meters cubed over moles. And then, don't mind my scrolling, we have that our molar volume is 1.4859 times 10 to the negative 5th power meters cubed per mole. Now I'm going to go ahead and put a box around this just to make it easier to find later whenever we are trying to plug everything in. Okay, so now that we have that, our next step will be, and I'm just going to go ahead and scroll up so that we have a little bit more room. Our next step will be to find our delta P in pascals. Now the reason why I want to do that is because you may remember 1 bar is equal to 10 to the 5th power pascals. Okay? And 1 pascal, like I said a minute ago, 1 pascal is equal to 1 Newton per meter squared. And the reason why that is because a Pascal is a pressure, and pressure is equal to force over area. Okay? And then the reason why we want that is because, like I said a minute ago, 1 joule is equal to 1 Newton times meter. So what we are going to do is we are going to first find our pascals. We are going to first find our delta P in bars. Then we will convert that into pascals. After we do that, we will use this relationship to help us find joules in the final equation. So the equation that we are going to follow is that delta P is equal to your final pressure minus your initial pressure. And then our final pressure, so we have P2 is equal to 1,000 bar. Our initial pressure, our P1, is equal to 1 bar. So if we come back over here, our delta P is going to be equal to 1,000, which is our P2, minus 1, and then I'm going to go ahead and put these in parentheses and put my unit out here since they have the same unit. So 1,000 minus 1 bar. And that gives us the answer that delta P is equal to 999 bar. Now I would like to go ahead and convert this into pascals at this point. So for our pascals, we're going to do delta P equals 999 bar. And then we will go ahead and say that 1 bar is 10 to the 5th pascals. And then you get delta P is equal to 999 times 10 to the 5th pascals, which of course we also know that means it is also equal to 999 times 10 to the 5th newtons per meter squared. Now that is the one I'm going to put the box around. And this is just so that I can find it easier later on. So if I were to scroll back up, we see that we have a box around this one, our molar volume, and we have a box around this one, our delta P. Now, the next thing that we are going to do is we are going to find our delta G sub M. And you may remember that the equation we're going to use for that is delta G sub M equals our molar volume, and we want that in meters cubed, times our delta P, which we want to be in newtons per meter squared. Now, our molar volume, you may remember, was 1.4859 times 10 to the negative 5. I'm going to go ahead and scoot this over. I apologize. I didn't give myself enough room. I write so big. And this is in the units of meters cubed per mole. And we know that our delta P that we just found is 999 times 10 to the 5th newtons per meters squared. Okay? And ultimately, what we want to find for our answer in our delta G, because it's the molar Gibbs energy, we want to find something in joules per mole or kilojoules per mole. Usually if it's over 1,000, this particular book will go ahead and convert the answer to kilojoules. So we will go ahead and just see what we are working with. I'm going to scoot this over just to give us a little bit more room now that we're done writing these. Okay, so our delta G sub m is going to be equal to 1.4859 times 10 to the negative 5 meters cubed per mole. I think I'm going to have to scoot this down because I write so big. Here we go. I think we can do it here. Okay, and we are going to multiply it by 999 times 10 to the 5th newtons per meter squared. Now, I always like to check my units. This is called dimensional analysis. I'm going to analyze the dimensions to make sure that everything will give us the type of answer that we are looking for. We want to make sure before we go ahead and put all of this into our calculator that we are even in the right track. So we want to make sure our final units will get us either joules per mole or kilojoules per mole. And so my meters squared here cancel out with my meters cubed, and I'm just left with meters. And then what I end up with is meters times newtons over moles. So it's going to be meters times newtons over moles. And if you remember, a meter times a newton is joules. So that would be joules per mole. So I'm going to go ahead and put this in my calculator because I believe that I am setting it up correctly. I'm going to erase this just for now. And let's see what answer we get. Go ahead and pause and see what answer you get. Okay. So what I got was 148 point, I'm sorry, 1484.44 newtons times meters over mole. And then we know that a newton times a meter is 1 joule. And it looks like this is going to be over 1,000 because we're just multiplying by 1 at this point. So let's go ahead and convert this to kilojoules. We know that 1,000 joules is 1 kilojoule. I'm going to cross out My units, my newtons times meters cancels, my joules cancel, and now I'm left with kilojoules over moles. And that is exactly what we were looking for. So we are going to put this into our calculator. Again, feel free to pause to see what you get. What I got is that our change in molar Gibbs energy is 1.484 kilojoules per mole. Now you may remember that the answer that the book gave us was 1.485 kilojoules per mole, but this answer is close enough. The difference is just due to rounding. So this right here is our final answer.